For a robotic finger, it is important to be able to complete both a curling motion for power grasps and a pinching motion for precision grasp. Our prior work more or less literally followed the Winslow's rhombus anatomical model of the finger extensor mechanism. The rhombus would open and close as it slid over the dorsal surface of the finger. We discovered that it was difficult to make this finger complete certain movements in free space by pulling the tendons, and tuning of the finger cross-section to adjust the kinematics was not feasible given the limited range in which the parameters could realistically be varied. The newer version of the finger, presented in this paper, dispenses with the opening of the rhombus, and in its place are two lateral bands that bypass the proximal interphalangeal joint in a similar way, with the origin and union, where they join at the distal end, represented by pins that run in slots on the phalanges. The origin is connected to the interossei tendons. As the flexor tendon is pulled without a great deal of interossei tension, the finger undergoes a curling motion, with the flexion distributed among the three joints rather than flexing one after the other. This would be useful in grasping a cylindrical object, such as a bottle. When the flexor tendon is pulled with more tension on both interossei tendons, the finger flexes with the phalanges outstretched, as in grasping a book. The finger can hyperextend with flexed interphalangeal joints. This finger introduces a new revolute joint at the metacarpal phalangeal joint, allowing it to adduct and abduct the finger in an anatomical range. We can query our kinematic model to generate sequences of tendon excursions needed to move the finger throughout its workspace. For example, we generated the trajectory shown that sweeps the fingertip in a loop along the outer boundary of its workspace. Because the finger is underactuated, external loads like gravity and friction can cause the poses to deviate slightly from those used initially to query the model. We compared this with a second routing of the lateral bands, in which the lateral bands passed volar to the mechanical stop. This had slightly different kinematics and was less prone to the mallet finger pose upon extension. Contraction of the flexors produces a power grasp, and co-contraction of the interossei produces a precision grasp with fingers outstretched.